you'll use these or not, since I'm cracking the whip and making you turn up here. It's kind of may defeat the object. I'm not quite sure. But anyway, all right. So let's start this. So we've talked about the mechanisms for transport. They are advection and dispersion. We've talked about how dispersion occurs, and it's due to two processes, right? It's due to molecular diffusion, which occurs which is significant if flow velocities are very small or zero, because then you see that as the major transport mechanism. But if flow velocities are large, then molecular diffusion gets completely swamped by mechanical mixing. And mechanical mixing just happens to look like diffusive process, and that's why we lump those two terms together, because when we talk about dispersivity, right, we talked about longitudinal dispersion, and it's these two individual portions that we look at. A longitudinal dispersion coefficient and multiplied by some advective velocity, typically along the direction of flow. And we can do the same for transverse dispersion. So two mechanisms, advection and diffusion. If we look at dispersion/diffusion, then there are two mechanisms embedded in that. One is molecular diffusion, very small, maybe 10 to the minus 9 meters squared a second. And another term, which we've already alluded to, is a function of the advective velocity, and also something that we've kind of said that isn't a material property at all, which is kind of intriguing. So we'll get to that later on today. So we know how to use those because we've developed the expressions on the board. We've talked about how we can use those to predict, for instance, what the magnitudes of dispersion would be. So now the question is, how might we be able to measure those values, to know what those values are, so that, for instance, we know that this isn't a material property, but it's related to something else, or how would we measure the molecular diffusion in our particular porous medium. And so you can imagine there are a variety of ways of doing that. You could do it in the laboratory, which is one way to do it. You could do it in the field in either of two ways. One is by using some kind of well test, so where you induce some flow. And we can think of a couple of configurations for doing that. And perhaps the best one of all of these, not always at your disposal, is to do something that kind of replicates the flow gradients, the flow velocities that you have naturally in your aquifer. And so what we'll find out perhaps is that by far the best is this last one, and indeed the other two might not be suitable whatsoever. That may well be the conclusion we're coming to. So talk about laboratory approaches. I don't want to talk about this. Not going through all of these. You can fill this in yourself. So here's the idea. So actually we've kind of couched the analysis that we did in these terms all the way through our discussion. And that was that if we want to look at an aquifer, then we can think of the aquifer as sitting beneath the ground level. Looks like some spill in the upstream portion where we have concentration of C0 at the upstream boundary. And we look at the behavior at a compliance point where we just we're removing water and we're measuring the concentration and how that concentration changes as a function of time. And so we can look at that either as a profile of the concentration along the sample or the aquifer, which we know how to do, or we could look at it at the compliance point where we get the change in concentration responding to time. For big Peclet numbers, infinite Peclet numbers, which physically mean, since the Peclet number is equal to the ratio of advective velocity to dispersion, when dispersion is 0, then the Peclet number is infinite. So that's the other way to think about this, right? As Lauren drew. And as dispersion is increasing, it gets flatter because the Peclet number is reducing. So obviously, if you do an experiment in the lab, in a core, you can't see this. And so you can't use that. But you can use the external residence time distribution trace as it comes out of the sample to be able to do that. And of course, what you could do is you measure the relative concentration as it comes out at the end of the sample. You normalize it maybe relative to the maximum concentration that you get out of the sample, which should be the same maximum concentration that goes in. You record what those magnitudes would be as a function of time. So you take a measurement here, maybe it has 0 concentration. Take a measurement here, maybe it has some concentration, and it ramps up to some magnitude. Of course, you wouldn't have this curve to be drawing on. You'd just be drawing a series of points with time. But rather than drawing these points with time, I suppose what you'd want to do is draw them as a function of residence time distribution. And so, as you just so rightly said before, your time would just be modulated by your advective velocity, which hopefully you could measure. If you know what the Darcy velocity is and the porosity, you could certainly measure the advective velocity. And conveniently, dispersion doesn't turn up in this term at all, so you don't need to know that a priori. And so this is the length of the core. This is the advective velocity that you induce in the core. This is the time at which you take your measurements. And if you plot it on that, you would get a curve. It would plot somewhere on one of these curves. And so from that curve, you'd end up with a value of you'd end up with a value of the appropriate Peclet number, right? Because we could make a whole series of these curves for every conceivable Peclet number that you might think of. And so you could see which this fitted best to. And since you know the Peclet number is equal to the advective velocity, which you know the length of the sample and the dispersion, longitudinal dispersion coefficient, you know this because it fits onto one of these particular curves. So in other words, this would be the Peclet number equals whatever. So you'd know this number. You'd know the advective velocity because you're putting it through at that rate. You know the length of your sample. And the only other term you have to calculate is dispersion. And so you can do that just from the expressions that we've used already. This happens to be a simpler form of this written in terms of pore volumes, but you're basically using that behavior. So this is what this U value down here is what we've called TR so far. And so that would be fine. And it turns out not to be fine. And the reason it's not fine is because a lot of certainly you'd get a value of dispersion in here. And of course, this value of dispersion would be a function of both of these mixing processes, if you like, that we've talked about. Advective velocity and longitudinal dispersion. And so you have to deconvolve this some way. And this certainly would be of the order of a small number, order of 10 to the minus 9 meters squared a second, which is molecular diffusion rates for liquids in liquids. And so if this number turned out to be a big number, maybe 2 or 3 or 4 orders of magnitude larger than this, then almost all of it would be due to this magnitude. And you could, of course, if you know the advective velocity, you could calculate the one remaining component. And so you could calculate what this dispersion coefficient was from that. It turns out to, certainly you can do it, and it turns out to be of questionable use because it, as we'll find out, the value of this dispersivity, if you like, is typically, I want to say proportional to, and of course the proportional to function is alpha, right? So we can't do that. So it's roughly equal to the length of the core sample divided by 10. And so this is what we alluded to and we'll get to later on, is that this is actually not really a physical property of the aquifer. It's much more related to the length of the sample. In other words, the length of this particular core. And so that's a curious observation. So it turns out that doing these kinds of experiments aren't very useful if you're talking about mechanical dispersion. They're much better if you're talking about Brownian motion or molecular diffusion. But then the problem is that because this number is so small, if you're doing this for your senior thesis, you might not have enough time to do a test before you take a single measurement, right? If the length of the sample is too long. And you could calculate, for instance, how long that would take just based on this. Right? And so the problem in doing this experiment is that the numbers you get out of this aren't so useful. So I mentioned that just to make the point that doing experiments on cores in the laboratory might be useful for measuring diffusion, but are not very useful for measuring dispersion because you don't get decent numbers out of it for the reasons we've mentioned. So the alternative to doing that is to do something else, and that is, instead of doing things in the laboratory, it's to do well experiments. And they're partially better, but they're not much better, and for that reason they're very rarely done. But let's just talk about two different ways that you could imagine to do experiments and talk about their drawbacks. The idea of this is a single well tracer test. You could imagine you take a well bore, you mix some sodium chloride in water, you pump it into the well and into the aquifer. It spreads laterally out from your aquifer a certain distance, and then you stop pumping in. Maybe you leave it for some time, and then you start sucking it out. And so you suck it back into the well bore, and as you bring it back into the well bore, you measure what the concentration is that you're bringing back into the well bore. And you'd expect it to look like something. What would you expect it to look like? So if you look like time, I've never really thought about this, but if you look at time versus relative concentration, you've pumped it in, and at this point here you start pumping it out. Well, I guess you'd have some kind of concentration distribution in space looking like what? This, I suppose, right? This would be around the front somewhere, or the front might be the 50% mark on this relative concentration, C over C0. This is radius in this particular case. If you now start sucking this back into the well bore, then you see the stuff that's the highest concentration first, and so you'd start right up here. And then as time went on, you'd get some kind of constant, and then it would tail off to some magnitude. And so the idea is, if you know what the solution is for the relative concentration and how that changes with the pore volumes as you start removing it, you should be able to calculate exactly what the magnitude of the dispersion coefficient in this is, because this expression has the value of that. And so we could explain how to do that, but I'm not going to. I'm not going to because it's not very useful, and no one ever does it. But it's a way that you could physically do it if you needed it. And again, the main limitation of doing that is that the dispersion, it won't measure diffusion, because you'd never be able to pump anything into a low permeability material to be able to do a test if this was a clay, for instance. So it would only work in sandy aquifers or silty, sandy, gravelly aquifers. And the magnitude of this dispersion coefficient you get is not really representative of the behavior, because it's a function of the scale of the measurement that we've kind of alluded to. So this doesn't work for you either. So you could do a more sophisticated test that now, you probably know from, if you remember from talking about your 452 class, if you ever talked about doing well tests in that, there are a variety of different well tests you can do. So you can do a slug test. You take a single borehole, just like this past one. You push fluid into the well. You measure the rate at which it goes into the well, and you use that to calculate what the permeability is. Or you can upscale, and you can do a full well test, where you drill a well, you just keep on pumping out of that well, and you measure drawdown at some other location, the so-called Theis solution that you might have used. I know people have used that in the past. And the idea is that if you want a representative value of the permeability of your aquifer and how much storage it has, so you can make some decisions about your... I don't want to do that. I was just shutting it off. So that you can make some decisions about your sustainable use of that aquifer, if you're going to use it for agriculture or for the water supply of State College. Then the idea that you have a pumping well and a monitoring well means that the volume you're affecting is much larger, and therefore it's a much more representative test because you're sampling a much bigger part of your aquifer. And so you could think about doing that for a well test that, instead of measuring the permeability of a system, attempts to measure the transport properties, the contaminant transport properties of a medium. So you can imagine putting in a well here. So you're looking in plan view, an injection well here, a withdrawal well here. You inject water that happens to have, well, it could just be water for that matter, right? Just straight water. And you can imagine that the flow field you get from this is this potential flow field that, we talked about fluid kinematics in Phi 303, and you could calculate what these are. You could surmise that you could get a solution for this. It doesn't really matter what the solution is, but you could surmise that the residence time from a particle of water going from this point to this point, the fastest way is the kind of as the crow flies direction. The gradients will be fastest along this flow path, and also it's the shortest flow path. And as you go further out, the slower flow paths will be these progressive ones. This one will be slower than the inside one. This one will be even slower. And of course, the slowest one is this one here, which goes off to infinity to your left, and then magically comes in from infinity to your right to the well. So that's infinitely long. And so if, for instance, you then, instead of just pumping water through this, you put some salt solution in it, and you looked at how quickly that salt solution arrives at the recovery well. Well, if it gets carried by the advective velocity on this streamline, it will arrive first from this well here, from this streamline. And as you go progressively on each of these other flow paths, then it will arrive progressively later. So if you think about a stream tube, which is between these two arrows, in other words, in this one here, you could look at the progress of the front as it worked its way along here, and all of a sudden it would arrive at the wellbore, and at the time it arrived at the wellbore, the concentration would start going up from 0 when it hadn't reached there to some small value once it just got there. If you look at the flow along the next kind of flow stream tube, as you get here, it would take longer, and so this one's already arriving, the next one's just begun to arrive, and will keep on arriving, and so it goes up and the concentration increases. So as you start adding more and more of these well tubes that actually arrive at the recovery well, then you start stepping up this. And if you keep on going, you can imagine that finally you'd reach some steady concentration that would represent the behavior here. And so you could imagine that you could use this curve. So this curve here, this is for the constant injection of fluid at some concentration. So in other words, the top one of those diagrams on the left side of the board, the heavy function term, in other words, the input function on this left-hand side with time looks like this, C over C0. And if you look at the output function, it would look like this, which is similar to one of the curves on the thing that we drew. If the input function was this spike function that looked like this, whoops, should be just vertical, again C over C0 and time, then the arrival response would reach some peak, and then because it's all worked its way through from the upstream well to this point here, it would start falling off. So you'd expect to see some distribution for this continuous injection case, plus the one where you just spike the fluid initially with a bit of ink, and then after that's pumped through, you just keep on pumping water through instead of ink, and you'd end up with this. So what's the problem with this for an experiment? Why would that not work very well if you wanted to measure dispersion? Well, the principal reason is that if you think about what we just said, how we do this, this is kind of looking at plug flow, right? The plug flow goes along this stream tube. It gets progressively further. There's actually no dispersion attached to this in our kind of thought of it, but it arrives here, and then it arrives at some low concentration. And it's only after this one has arrived that the next one will arrive and do this. And so if you think about it, basically there's some natural dispersion in the system, not because it's flowing in this porous medium and mixing and spreading, but because it's arriving fastest in this stream tube and slowest in this other stream tube and even slower in this other stream tube. And so if you think about it, it's kind of like the case if you look at what we think of as our idea of dispersion is that you have this front going through here with these fingers attached to it. And this is C0 back here, and this is concentration equals 0 ahead of this, is that these, of course, are flowing along fast paths, and they arrive early, and they do something to this behavior. But this hasn't happened because of anything to do about the natural process of this occurring in the aquifer. It's happened purely as a function of the geometry of the flow regime. And so you'd imagine that if you use this to try and calculate the dispersion, there's this huge effect of the dispersion just of the geometry of the flow regime, and then on top of this there'd be this mixing due to this hydrodynamic mixing, which you'd have to pick out from this other big signal. And so the issue is this signal completely overwhelms any dispersion that you'd see due to mixing in the aquifer, and therefore it doesn't work. And so for that reason, when we come back to these discussions about how we might want to measure these, laboratory methods work okay for molecular diffusion type things. Well testing, either single or dual well testing, doesn't work very well for these because the scales are too long and you have to wait forever to see it, and they also don't work for values of this dispersion coefficient. And so typically they're not used for that. And so where does that leave us? How do we do it? How do we get magnitudes for these in some cogent way to be able to design the projects that we'd like to be able to look at? And so one way to do it is by so-called natural gradient tracer tests. And so the idea here is that you do an experiment or you measure an existing plume, and if you know, for instance, when that plume originated, you certainly do if you run an experiment to do it, if you put it in the ground yourself, then you can do something hopefully to be able to figure out exactly what the dispersion coefficients are. And so here's the idea. This is also taken out of your textbook, out of Fetter. It's from an experiment that was done in Borden, in a couple of hours north of Toronto at a Canadian Air Force base, as it turns out, which is a sandy aquifer. And what was done was that a plug of tracer was put into the very shallow aquifer, maybe a meter, 2 meters, less than 2 meters, yeah, a meter below the ground surface. The water table is quite shallow. And surprisingly, this isn't such an easy thing to get, obviously, that you have this picture of where this plume has gone from when it was initiated at 1 day to where it was after, I think that says 85 days, to where it was after a year and a third, to where it was at almost 2 years. And so this is exactly the behavior that we've seen if we look at, for instance, what we said we thought would happen if you put tracer in the ground, in that it would move from an injection point here to downwind of this, to downstream, to further downstream at successive locations. And so what we could do, since we know that the dispersion of this plume is a function of this 3 standard deviations of the Gaussian distribution, if we can find the edge of the plume and we can measure exactly what this length is, we have a chance of being able to figure out exactly what the dispersion is. And we hope that because it's being driven by the natural gradient, which sits in situ anyway, that if we measure this and we know when we look at what the plume looks like, then we can pull this value out of it just by solving this equation. And that's really all it is. And so what we can do for these particular cases is we can use that, and that's all this tabulation to the left is. We need to know, what is it we need to know? We need, what was it, that 3 standard deviations was equal to the square root of, I guess I have it here since I didn't write it down. Is it on this page somewhere? Yeah, it is. 3 standard deviations is equal to 3 times the square root of 2 times the dispersion times time. And so if we measure these values, so if we measure this length, it's easiest to measure on this one here, for instance, but you can do it on all of them. This length here, after 647 days, if you can see that, is of the order of 61 meters. No, sorry, this is how far it's traveled. And Well, that's, oh no, okay, yeah. Okay. So the other thing we'll need to know is the advective velocity. The length of this, I guess, after 647 days is 15 meters. So this length here is 15 meters. So this is 10 meters, this is 15 meters, so that's, sounds about right. Maybe it looks less than that, but it doesn't matter. So if you know what the magnitude of this length is, you know that it took 647 days to get that big. It started off very small, but by 647 days, then you can just use this expression here to be able to figure out what the value of this dispersion coefficient is, and you evaluate this magnitude. So you get a magnitude, in this case, of dl. This is our dl value, d sub l, longitudinal dispersion. The other way that we classified dispersion coefficients are due to this other expression, you'll remember, right? Is just molecular diffusion or spreading by molecular diffusion plus the advective velocity, or at least the absolute value of it, times the longitudinal dispersivity, I think it's referred to. This is in units of meters squared over time. Could be days, typically as seconds, but in this particular case, since these are in days, it's perhaps easier to do. And so if we assume that, well, what value do we have for this? So this is of the order of 0.02 meters squared per day. What order of magnitude is that if we look in terms of meters squared per second? Hello. Question.
I want to know where the bathroom is.
Oh, that's fine. Too much information. Too much information. What's the value of the dispersion coefficient in meters squared per second? Good time to leave. Did I see something there? I wasn't sure what that. I caught something in it. I was always interested to see how this one picture of my kids, my daughter standing there like this when we made them actually have a picture taken. So I could. She's your age, so a year older perhaps. Where were we? Oh, are we recording this? Oh, thank God we're not on camera. So, for many reasons. So what we'd like to, so the point is that we've got a value for this. We'd like to deconvolve it from these two different parameters which we don't know. The only way we can, for instance, exclude this is if our value for dl, dispersion, is very much bigger than the value we expect for this, which might be, we've said, is of the order of 10 to the minus 9 meters squared per second. So the question is, if this is in 0.02 meters squared per day, so it's 2 times 10 to the minus 2 meters squared per day, what is that in meters squared per second? Is it big or small relative to this? And so how many seconds in a day? 86,000 something. So it's 10 to the minus 5. So good number to know. So it's 2 orders of magnitude. This is 2 orders of magnitude larger than this, right? Roughly. And so the main contributing factor, so basically this is 0 in our calculations. Great. So now we have one number which relates to another number. If we know the value of the advective velocity, we have a chance of being able to calculate the longitudinal dispersivity. And so that was this calculation here. It's gone 61 meters downrange in 647 days. What's the velocity? Well, it's 61 meters divided by 647 days, or for these different ones, it's of the order of 0.09 meters per day. And so now that we know this, and we know this, then we can calculate the value of this longitudinal dispersion. And if we do that, we end up with some number, which I don't report here, but you could do the calculation. So we can find out what it is. Of course, the other thing you can do is you can also measure this behavior transversely, right? And so the two aspects of this would be kind of the longitudinal length, which is what we call 3 sigma x, and the transverse length, which we're going to call 3 sigma y. And you can do the same calculation with these other widths. And if you use that, you can calculate what the transverse dispersion is. And you see that these values are different from each other. We said before that maybe they're a factor of 3 different. This is always smaller than these. And that is of the order of magnitude, right? So that. Well, not in this case, right? Because this is actually roughly equiaxed. But as you go down gradient, then the ratio of this to this, what's that? 4 into 23, that's about a sixth, right? 4 into 19 is also about a factor of 4 or 5 or whatever. So they're different by that amount. And so that's why when you see these plumes developing like this, they're elongate in one direction because dispersion is larger in the longitudinal direction. Okay? All right. And so that is our preferred method of being able to do this, either for purpose-built experiments, which are rare, or by looking at our plume in situ and estimating from that. Of course, actually, these are really unusual measurements. Why do I say that? Any thought why I say that these are? Is it normal to know what a plume looks like at that level? It's not usual to have that much information or data. And so the reason is that these experiments were done in a very shallow aquifer. It was done in a sand aquifer. And basically these concentrations were measured by just taking capillary tubes, so maybe a 1/10 of an inch diameter stainless steel tubes, physically pushing them into the ground, and then just sucking water out in them, and then measuring the concentration of the water that's pulled out of them. And so that's very easy to do if you kind of roughly know where you are. If you know what the advective velocity is in terms of its direction, then you know that the plume is headed off in this way, and you just have to, and if you know what the hydraulic gradient is, and you know what the permeability is, and you know what the porosity is, you can make the first estimate of where you should at least start looking after 83 days or after 462 days, right? It's just going to be, this length is going to be equal to what? Advective velocity times time, I think, right? Just as you've done, to get some idea of exactly where you should start looking. And then once you found it, then you just work out from there to cover the field. Okay? All right. So we've made the point that in aquifers where there's relatively high flow velocities, there's going to be this dispersivity term, and this is going to be still there but completely swamped. In aquifers which have very slow velocity, like clays and shales, then this term, even though it's small, will be significant because this term might be 0, and so it may be the dominant feature. We made the point before that maybe this actually isn't a material property whatsoever. And so do we have any data to support that? Well, we may do, right? We've measured this, we've tried to get the value of this dispersion coefficient for 3 different magnitudes, for 3 different times rather. We know the advective velocity is probably staying the same for each of these. Is it? I guess we can check that. Well, roughly. From 9 to 11, from 8 to 11, right? So it changes by maybe 20%. But the magnitudes of these dispersivities are changing, well, actually they're not too bad, right? So that they're changing from a low of 0.016 to a high of 0.023. They don't show a trend in that this isn't the, one isn't, I mean, this intermediate one is the largest one, rather than, and the earliest and the latest ones are the smallest, so there's no real trend in there. With knowing, well, we might expect this to be a larger value, and for reasons that we'll talk about now. But so we've made the point that this is not necessarily a property which is a function of the aquifer. Actually, these data are kind of non-conclusive, right? They are kind of similar to each other in the range of values that we're typically talking about in this class. We've said that permeabilities vary by 6 orders or 10 decades, 10 orders of magnitude, but these are actually quite close to each other. What do we think is going on in these systems? Well, we've alluded to it before. And what we've alluded to is the fact that individually within the pore structure, we might have flow velocities occurring between grains where it's slow at the edges, at the pore throat edges, large in the middle. And so you'd expect this to give a high velocity in the middle, which should carry stuff downstream quickly, and less velocity at the edges, which would kind of leave it not traveling very far, and there'd be some spreading that would occur with this. If you take that and kind of think about the connected high velocity pathways that you might have in this, maybe a lens of material with a higher porosity or larger grain sizes, then you'd expect that the stuff that's being carried by the water would travel faster in this zone than it would around it, and therefore would result in spreading as a function. And that's exactly what happens. And so the mechanics of dispersion is responding really to the fact that you have this heterogeneity within a system which allows some areas to travel faster than others, and as a result you get some spreading occurring as a result of that. And so you get some very interesting behaviors if you look at, for instance, looking at a whole bunch of observations from natural gradient observations. And so this is exactly what we've talked about doing today. So we've just gone through the case of trying to figure out exactly what dispersion coefficient should be for this Borden site. And we calculated the value of this longitudinal dispersion out of it. If you did that for a whole bunch of other sites, whether either natural contamination or human-induced contamination, doesn't particularly matter, and you plotted up the magnitudes of, say, the length of the plume in meters, in this particular case, and you plotted up the magnitude of the dispersivity you got from this. So this is dl is equal to molecular diffusion plus the velocity which you have in your particular aquifer times this thing that you'd perhaps think is kind of a material property, right? In a given aquifer, it would have a value. And if you went anywhere in that aquifer, it would have the same value. But what turns out, if you calculate this magnitude of this longitudinal dispersivity, which has units of meters, right? Because this has units of meters per second, and so together they have units of meters squared per second, right? The product of these two. If you calculate this magnitude and plot it versus the scale, how big the plume is, you end up with this scatter plot. It's almost like shooting a shotgun at a barn door to some respects. There's lots of variability, but you can draw an upper bound on it. And you could draw a lower bound on it. And you could draw a line that goes somewhere through the middle of it. And this line that goes somewhere through the middle of it is roughly plume length divided by 10. And so that's interesting, right? It says that it has it might have some correlation with the aquifer, but it has more of a correlation maybe with the length of the plume that you find. And so why would that be? What would be a rational reason if you thought that was the case? What would make sense? So it's talking to the fact that it doesn't care about the material that's in the aquifer particularly. But I suppose it's saying that some characteristic of all aquifers are the same, and those properties vary with scale. So what do you think? No thoughts? No thoughts whatsoever? Okay. Well, I think one way you can interpret it is that if you think about this stuff flowing downstream, plume starts off small, it sees some little pieces of heterogeneity, and you find out these little fast pathways, but maybe they're just small features. So maybe you're sitting in your aquifer, and you're at this upstream location, and maybe you have some little features like this, which act as little fingers, which allow this to actually speed down here. But now as you go further out from here and the plume grows, maybe you have in your aquifer the chance of you being able to hit a much bigger feature, like a fault, which is much bigger and has a much bigger permeability contrast, all of a sudden is much higher because you're sampling a much bigger patch of your aquifer. And as you go even outside that, then the chance of hitting a really big open fault is perhaps even larger. And so the idea is that as this, the size that you sample in your aquifer increases from some very small magnitude, maybe a meter in size, it only has a chance to sample some of the small-scale heterogeneity and not really big distributions or differences in permeability. When it gets to 10 meters or 100 meters, all of a sudden the chance of it hitting a big feature is much higher. The chance of that being a really high permeability compared to the kind of average permeability of the system is also much higher, and therefore the spreading that you get for going on that fast pathway is much larger as well. And so that's kind of the interesting feature that comes from that, and that's the reason for it. So quite straightforward, but also quite surprising, because this says that it doesn't matter whether it's a sandstone, a gravel, a silt, a fractured sandstone, that within the realm of this distribution, it doesn't care what the material is at all. It just cares how big the plume is. And of course, you have to take that with a pinch of salt, because of course, if you have a plume that's 100 meters in length, then the magnitudes of dispersion aren't just the value of this parameter here, but it could be 2 orders of magnitude larger, or it could be 1 order of magnitude smaller. And so this span here is 3 orders of magnitude. So this is a reasonable approximation, but maybe not always good enough, right? Depending on how well you need to know exactly what the magnitude of that dispersion coefficient is. Okay? All right. So I don't want to stop there. You'll be unhappy to hear. But I will take a 2-second break because I might split the movie down the middle. So I'm going to come back to this. So we've kind of talked about contaminant transport. We talked about mechanisms of transport, advection and dispersion. We've talked about 2 mechanisms of mixing, which are mechanical dispersion and Brownian motion, molecular dispersion. We've talked about how to get magnitudes of spreading for different flow geometries, either plug flow down a core, spike flow down a core, and also this kind of 3-dimensional case. And we've talked about how both the values of molecular diffusion and dispersion can be pulled out really only by 2 methods, right? Mechanical mixing from natural gradient experiments, but we can also use this correlation that we just talked about to do it. And for molecular diffusion with the added effect of the tortuosity of the pore space, maybe we can get that in measurements in the lab, and maybe not. So we know something about it. And so we know how to be able to make predictions on, for instance, what these plumes might look like as they evolve and we look at some kind of compliance point. So we know how to do that. So